All right, let's get to it. This won't take long. It should take, here, I'll time myself. I should be able to knock this lesson out in 13 minutes. I say that, but there it goes. All right, let's go. 27th. Hey, turn on. And we're going to accomplish two tasks today. One is we're going to plot or graph complex numbers. And we are also going to find the modulus of complex numbers. The plural of modulus is moduli, so technically I should be saying we're going to find the moduli, but yeah, you're not allowed to say moduluses. It's like saying vertexes. So to keep the grammar on point, I'm going to say modulus of a complex number. I can't pluralize complex numbers, or then it doesn't really work. So there you go. That's the goal for the day. First, and this should not take any longer than, oh my goodness, I almost hesitate to even teach it to you, but here we go. You have to know how to plot a complex number. And so to plot a complex number, you use the complex plane. It's kind of like the coordinate plane that you're used to. What you guys have always graphed in is the Cartesian plane, the X and Y, named after Rene Descartes. Okay, so when you see an X-axis and a Y-axis, that's a Cartesian plane. When we graph complex numbers, we graph them in the complex plane, is what we call this. And we rename the axes. They are no longer X-axis and Y-axis. The artist formerly known as the X-axis is the real axis. And the artist formerly known as the Y-axis is, you probably can guess, the imaginary axis. So from this point on, like if we're graphing, if we were in like algebra 1 graphing a line, we would graph it on the Cartesian XY plane. We're working with complex numbers, we switch and use the complex plane, where now the axes don't represent X and Y values, but rather real and imaginary portions of a number. And it is exactly as easy as you might think. That you're thinking like, there's no way it's this easy. Yeah, it is. So if I said to plot the number, the complex number 2 plus 5i. Yeah, I know you do. Yeah, where are we going to go? Don't say over. I hate that word. Right to. Thank you. And that's it. So we leave the complex origin and we go right to and up 5. And that is how you plot a complex number. You just plot it, aware of the fact, though, that you're not plotting it in a Cartesian plane. You're plotting it in a complex plane. Okay. How would I plot the complex number negative 4i? Hey, let's see if you remember this from Monday. What do we call that kind of complex number? It's called a pure imaginary. It's pure. It's purely imaginary. You just go down 4. So like if this one actually sits on the imaginary axis, you just plot it right there. And then here comes a complex number, one that you generally wouldn't say is a complex number, but it is. 7 is a complex number, right? It's called a real number. Very good. And so I would just simply go right 7. And that is that. Don't you start with me, Corbin. I hate it just as much in algebra 2 as I hated it in algebra 1 because they go over 3.
Which way is all about respect.
What's that? Like this. So that's the first part, which I think you agree doesn't really deserve any more of our time. So when you plot a complex number, there's really no more meat on that bone at all. It's just you're thinking of it like X and Y normally would have been, but the real part is your left or right, and the imaginary is your up or down. So the second part of the lesson is a little bit more interesting than that. So to find the modulus of a complex number, let's start with the yellow one. So what a modulus is, and I used to, in my younger days, make the mistake of calling it the absolute value. It is not. The absolute value is not a term that's applicable to something like this. What we're literally finding when we find the modulus is how far that particular complex number is away from the complex origin. And you've seen this concept before. You guys all had to have taken geometry at some point, or maybe you're taking it next year, I guess, right? Sorry, my bad. But you've probably seen some semblance of the Pythagorean theorem, right? So the trouble is when you want to find the distance of a crooked line like this, you can't just count it, right? Because you can't count crookeds. So we use a squared plus b squared equals c squared, right? So if I wanted to know how long is that yellow line segment, then I would need to know some other things. I would need to know, well, the length of this yellow line segment that I'm drawing down here. And I would also need to know the length of this yellow line segment right here. And what's significant about those two that I just drew? Yeah, they make a right angle. And with right triangles and right angles, then we can bring in the Pythagorean theorem, which tells us that a squared plus b squared equals c squared. So the fact that there's a right angle right there in that corner, let's see if I can actually make it into a pen. There we go. Good job. The fact that that's a 90-degree angle brings into play a squared, b squared, c squared. And in case you have never heard of the Pythagorean theorem, it just simply is a useful tool that enables us to work with side lengths of triangles, provided though that they have a right angle. And so the A in this case, I usually just by default call A the very shortest. Which one can't change? C has to be the hypotenuse, right? The crooked one, the one across from the right angle. So when we talk about a squared plus b squared equals c squared, let me erase and give a little workspace here. So when we talk about a squared plus b squared equals c squared, A and B are negotiable. Like they can swappy, swippity, swappity, but C is like, no way, I'm the crooked guy, right? I'm your goal. So A and B could be short, long, long, short, as long as they're the right angle guys. So in this case, I would probably just define A to be 2. You don't have to go through all this every time, by the way. I'm just trying to give you a little background knowledge. What would B be? 5, right? Good. And so when we plug that into the Pythagorean theorem, a squared plus b squared, what is a squared? And what is b squared? Good. And then when we add those, we get c squared, and 4 plus 25 is, of course, 29. And if 29 equals c squared, then what is c? It's just straight up the square root of 29. And we're not interested in 5 point something, right? That's not where we're going to go with this. So we would just call it root 29. So in a case like this, here comes the math problem, okay? Get this into your notes. I'm going to scroll this. I'll come back to that in a second. The way this would look as a math problem, watch the TV right now because I'm going to add something. I want to make sure you catch it. It's going to look like the absolute value, but that's called the modulus. The modulus of that complex number is equal to root 29. Got it? And again, I Googled it because I wanted to make sure once and for all that I'm just not allowed to say it a certain way. And it is definitively the modulus, not the absolute value. Those aren't interchangeable. Good on that. Simple. You can see that we could have worked this a lot quicker instead of drawing the triangle. I just wanted you to see the triangle one time so that you know what's going on behind the scenes. This isn't just like some voodoo thing that we're doing here. It's just an application of a simple formula. So let's take a look at something simple, like the green one. So I don't need a formula for the green one. And as you'll see, as you go through, these are your favorites because what is the modulus of the complex number 7? Yeah, and I can count that out. I don't need A, B, and C to tell me that I just have to walk 7 steps to the right to get to that guy. And that feels pretty absolute value-y right there, but we are still in context talking about, you know, a distance on the complex plane. So we still call it modulus. And of course, another simple one is what is the modulus of the pure imaginary negative 4i? It is just 4. Again, I don't need a formula. I don't need a triangle. I don't need anything. I just need to be able to look and say, well, I just have to walk straight, literally straight down 4 steps to get there. It's a distance at the end of the day. That's what it is. Any questions so far? Okay, I'm going to knock through some examples with you real quick on modulus, and then it's go time. And I'm at 9 minutes. I think I'm doing great. So let's get to it. Modulus of 4 minus 7i. Ready, go. You can picture, if you, not that you would close your eyes, but it feels good because I'm sleepy. So if you did close your eyes and look at it, you'd see a triangle with right angle sides of 4 and 7. And you could just do the a squared, b squared in your head. What's a squared? Good. So we're building a square root first off. Let's just get this out of the way. We know it's going to go in a root. Just do it right now. So we're going to go with a 16. And what's the b squared?
42.
And you always add those together because a squared plus b squared. And what's 16 plus 49? And that's it. Root 65 is the modulus of that complex number, which approximated would be 8 and change. But again, that's not what we're going for here. How about this one? The modulus of -1 plus I. So we know it's going to be a root, right? Form good habits, you guys, and just make your root right now. You know, I won't ever tell you to do anything that's for any reason other than just to help you. So start by just making a root. Just get it done. Root it. So what's a squared? What's b squared? What's 1 plus 1? So the answer is root 2. What did you say? Yes, you. No, sorry, I'll slow it down a little bit there for you. How about this one? The modulus of 3 plus 4i. It's not a crime to start working these more mentally. These are problems where I do expect a lot of mental gears cranking. So anyone come up with like a final answer? It's 5. Good job, you guys. That's a 3, 4, 5. If you haven't taken geometry yet, Mr. Manlove will teach you about Pythagorean triples. Those are triangles that are always predictably fillable. You have a right triangle with 3 and 4 as the legs. 5 has to always be the hypotenuse. So whenever you see those 3, 4, you could just complete it with a 5. The process, though, shown for those of you that are like, slow down, chill, we just do it the same. A squared is 9. B squared is 16. 9 plus 16 is 25. And the square root of 25 is a nice pretty. Okay, how about this one? The modulus of 6 minus 2i. You're to the stage of the problem now where you should be trying to break down the square root of something, right? We've done it like this. We've done this so many times that we just know when we see the answer, let's get to it, that there's something wrong. Like we come to just recognize roots that need dealt with and roots that are just dead roots, right? So like the first few that we've done, we got a lot of dead roots. But in this case, 6 squared is 36. 2 squared is 4. And when you add 36 and 4, you get the square root of 40. And we just know our spidey sense just tells us like, that's not going to fly, right? What does that break down into? 2 root 10. Very good. Because remember, it was root 4 root 10, and then we rooted the 4 to make a 2. Okay. What's the modulus of 4? Good. What's the modulus of negative 18i? Just 18. Your modulus will never be a negative real number, okay? Because it's a physical distance. And then lastly, let's do the modulus of 5 minus 12i. If you really aced geometry and all of Mr. Manlove's wizardry about Pythagorean triples, you would recognize this one like that. Yep. There's all sorts of Pythagorean triples. They're, again, those packs of numbers that work very much in like great harmony and teamwork to make like we all agree to be whole numbers kind of thing. But if you don't recognize the triple, then you just do it. I'm giving you this lesson in such a way that no matter what you can or can't do mentally, you can always just do the process, right? A squared is 25. B squared is 144. That's 25 plus 144. And the square root of 169 is exactly 13. So as just a parting pro tip for you, you've already seen a couple of Pythagorean triples today, and you guys, ninth graders who go in next year, this will help you, okay? when you see Pythagorean triples, common ones are, here they come. You should want to know these. 3, 4, 5 is a very common Pythagorean triple. Another very common triple you just saw is 5, 12, 13. Do any of you by chance from last year remember any more triples? There's two more that for me always come to mind. They're useful. They're like little time savers. Another one that you might recognize is 8, 15, 17. Those three numbers together perfectly make a right triangle. And the only other one that ever really for me comes to mind, and there are infinitely many of these, but 7, 24, 25 is another Pythagorean triple.
But they have to go back.
Well, they have to go in the order in such a way that like the two shortest sides we indicate are the legs, right? They're the
Yeah.
right angle sides. Yep. So as long as the C is the longest one. And by the way, any multiple of those is also a triple. I'm just packing you with some good bonus knowledge here today. If you were to multiply all the numbers in the 3, 4, 5 triple by 2, then you could deduce that 6, 8, 10 is also a triple. Multiply them all by 3, 9, 12, 15 is a triple. If you're a multiple of a triple, you're a triple. And the same can be said of the 5, 12, 13. If you double them all, 10, 24, 26 is by default. Check it if you want. It's a triple. 10 squared plus 24 squared, guarantee equals 26 squared. And the same for all those. So if you know those four base triples, any multiple of them might be a time saver that you run into. Good. Do you have any questions on graphing? Any questions on finding the modulus? You're good to go. It's on the delta math. So let's use today to, if we're not done yet with assignment number 49, maybe it was, get that done. And then also today's, I think, is 50. Get that done too. Get her done.